up until now, we've assumed that charges move instantaneously through a metal. We know that's not true, but we want to find out what's actually going on in here. So we're going to kind of go very, very in-depth, very first principles of what's happening. So we first want to kind of consider just a nice cylindrical wire. We can look at other things later. And we might be thinking about some amount of charge moving through it. So we might call Q the charge. Now, in a metal, we know that charges are the electrons, and the electrons are what moves through the metal. So our charge in this case is going to be just the number of electrons times the electron charge. Well, we know what the electron charge is. We use that as E. We can write that up over here. E is our electron charge. And our number of electrons, we're going to use a little bit of a weird thing for right now, but we're going to dump it nearly immediately, so don't worry too much about it. Capital NE. Now, capital NE is interesting because, right, we are essentially saying that we have some collection of charge and that we have NE in here. Now, there is a measurement in a metal of electron density, how many electrons per unit volume, that can be measured for a metal and stays constant for any metal. So we have something called N sub E, which is electron density. This would be capital NE over the volume. So then we can say that our capital NE is a little ne times some differential volume. So what we are saying is we're saying that inside of this volume, delta V, we have the electron density times the volume. But looking at this volume, we can notice that, right, our wire has an area A on each side, so it should have area A there, and then we just have some slight differential length, delta X. So actually our number of electrons we can also write as the area times delta X, that would be the volume. So then we'd have N sub E A delta X. So our charge then, Q, is going to be the number of electrons, NE A delta X, times the charge of my electron. So that's the amount of charge moving through any given point. We want to talk about the flow of charge, so we define I as dq dt, or as delta Q over delta T. So I have my delta Q NE A delta X E, and I'm dividing by delta T. So in this case, I can take a look specifically at delta X over delta T. So my delta X over delta T is called the drift velocity. It's a velocity, but we don't really use the drift velocity itself. We think of what's going on with the drift velocity. So we can look up what's going on. This is a shorter definition than the full thing. But what's happening in an electron as it moves through a metal is if it's being pulled to one side or another, it does have a general movement, but then if it gets too close to any positive charge, that charge has a huge force on it and essentially scrambles up the velocity such that it might start moving like this, might start moving like this, and so on. So what we can kind of do is say, okay, if it has a random velocity at the beginning and then it ends up with another random velocity, we kind of really just care about how it accelerates through here. We know that velocity is acceleration times time, or usually we say that acceleration is change in velocity over change in time. So we are saying that our delta X delta T is equal to acceleration times time. And this tau is our flight time. Now, what's cool about NE and tau is they're both properties of the metal. Any metal that we choose has a known and defined NE, has a known and defined tau. So if we choose copper, we can look up the tables what Ne and tau are. So now we have this for A times tau over here, but we also want to look at what A is. Well, A is the sum of the forces over the mass. And in order to get charges to move, we submit them to an electric field. So the force for an electric field is the electron charge E over E, and since our electron charge carrier is the electron, it's over the mass of the electron. So as we look over here, we can bring this down over here, and now we have NEA, and we replace all of this, right? EE ME times tau times E, all is our I. This is really ugly. One last little update, right? This M sub E, this is the electron mass. So every single electron has the same charge, the same mass. Any metal that we choose has a known Ne and known tau. So we want to take a look at this and bring it a little bit nicer. We have EE, so we have an E squared, N sub E, tau over ME, and then we have A times E. So this A is the area of the wire, and the E is our electric field. So looking at this specific term here, we see that once we choose a specific metal, E, N sub E, tau, and the mass of the electron should all be the same for a specific metal, because every single electron has this, every single metal has that. So we are going to define a new quantity, conductivity, and the conductivity sigma is going to be E squared N sub E tau over the mass of the electron. This will be the same for any metal, or for any wire of the same metal. And this gives us a much, much nicer, as we might expect, relationship here of our current is equal to sigma A E. So now we have a nice definition of conductivity. We can look up conductivity in a table for aluminum, for copper, for steel, for anything like that, and just look it off. And then we have the area of our wire and the electric field of our